Okay, hi everyone, welcome back to this video series for introduction to firewalls. So, okay, packet filtering. The first firewall products used only packet filtering to protect the internal network from outside users. The firewall inspected the IP header of each packet that entered the network and made a decision to allow or to block the packet based on the IP addresses used and the specific port number in the TCP or UDP header. Although this functionality is still the cornerstone of firewall products, packet filtering used this way is not enough to secure the network. Packet inspection needs to be smarter about which inbound network packets are expected in response to a legitimate request from an internal network user, and which inbound network packets are unsolicited and should therefore be blocked. When a firewall sees an outgoing network packet, it should remember that an incoming response is due soon and only to allow those expected incoming network packets. The remembered information is called state. This smarter form of packet filtering is called stateful packet filtering, as opposed to the original stateless packet filtering, which did not remember the state of expected return packets. Filtering IP data. Packet filters are rules that inspect the information in the packet header of every network packet arriving at the firewall so that they can decide whether the packet should be allowed in or out, or whether it should be dropped. If the packet is allowed to pass, it continues on its merry way. But note that an IP packet never passes any router or firewall without undergoing some modifications. Before the IP packet is sent on its way, the router or firewall reduces the numerical value of the time to live TTL information in the IP header by at least 1. If the TTL value, which the sender of the packet probably set at 128, ever reaches 0, the packet is discarded. Discarding the packet prevents endless looping of IP packets in cyberspace due to router misconfiguration or similar causes. Because the TTL field in the IP header changes, the value of the header checksum field must be recalculated and is changed as well. The IP packet may be modified even more when passing through the firewall. Later in this chapter, we show you how to add network address translation NAT to the firewall. In NAT, the IP numbers and port numbers that are used in the packet are substituted with other numbers before the packet continues. When the firewall also performs application proxy functionality, the network packet may not pass at all and instead be rebuilt from scratch and sent along. You can create packet filter rules that check the following fields in a network packet that arrives at the firewall. Source IP address. This is the IP address that the packet lists as its sender. This field doesn't necessarily reflect the true original computer that sent the packet. The field may have been changed for legitimate reasons by a lab machine between the sender and the firewall, or hackers may have changed the field, which is known as IP spoofing. Destination IP address. This is the IP address to which the packet is being sent. Make sure you list the actual IP address in the packet filter rule and not the domain name system DNS name, such as server3dummies.com. Otherwise, a hacker that takes over a DNS server can immediately pass all packet filters undisrupted. IP protocol ID. An IP header can be followed by different protocol headers. Each of these protocols has its own IP protocol ID. The best known examples are TCP ID6, UDP ID7. Others that you will encounter are ICMP ID1, GRE 47, which is used for PPTP connections, and ESP ID50 and AH ID51, which are both used for IPsec protocol. TCP are UDP port numbers. The port numbers indicates to which service this packet is destined. You should only allow ports that are associated with allowed services such as HTTP port 80 or FTP port 2021. The appendix contains a list of many well-known port numbers and their associated services. ICMP message type. ICMP is the housekeeping protocol of the TCP IP protocol suite. Some of the ICMP types are very useful messages. Others are very dangerous and should not be allowed to pass through the firewall. Fragmentation flags. IP packets can be broken into smaller packets to accommodate network segments that can only handle smaller size packets. Unfortunately, as is discussed later in this chapter, this functionality can be misused. IP options setting. IP options setting. Optional functions of TCP can be specified in this field. Hackers can exploit the source route option in particular. These options are only used for diagnostics, so the firewall should drop network packets with IP options set. Besides checking the fields mentioned in the preceding list, packet filters can also make a distinction between packets that are outbound from the internal network to the internet and inbound from the internet to the internal network. The network interface on which a packet arrives is an important criterion by itself. Because a hacker can easily forge the sender IP address in the network packet, the firewall can't really trust that information. However, if the packet arrives at the external network interface using a sender IP address that belongs to the internal network, the firewall should recognize the IP spoof immediately just by noticing that it arrives at the external network interface. ICMP. Many ICMP packets are useful in diagnosing network connectivity. The best known example is the ping application that sends an ICMP echo request to another machine. If that machine is available, an ICMP echo reply packet is returned to the ping application. Other useful ICMP types are the TTL exceeded and destination unreachable, which indicate that the packet did not reach the final destination. ICMP also has message types that can be dangerous. The ICMP redirect can be used to tell the firewall to use a different route to send packets to certain recipients. You should not allow this type. This is like Mr. C. Rook telling Doorman Sam to forward all illegal documents to the big chemical plant case to him instead because it's a quicker route. This ICMP redirect functionality clearly shows that TCP IP was designed in a time where all computers on the network were supposed to cooperate with each other in a friendly, constructive way. Actually, the original RFC 777 document that defines ICMP is dated April 1st, 1981. Go figure. The echo request, echo reply types also create a vulnerability if used by outside hackers to learn which computers and which IP addresses are available on the internal network. The firewall should block this outside initiated use of the ping functionality. If the firewall implements NAT, this vulnerability won't be present. So here you have table 3.4 shows a sample ICMP packet filters that allow ping from the internal network. So you can see here the direction in the packet filter is important because it distinguishes between the ping command that is initiated on the internal network hello and the externally initiated ping command deny. Fragments. IP network traffic travels over all kinds of network segments between the sender and the destination. Not all these segments or links may allow the maximum packet size. The maximum packet size is called the maximum transmission unit, MTU, of the network if a larger IP packet has to cross a network link that allows only a smaller size. The original IP packet can be broken into smaller IP packets and continue. These smaller packets are called IP fragments and are shown in figure 3.1. Each of these IP fragments has its own IP header that contains the source and final destination IP address as well as a fragment position, but only a small part of the original TCP IP information. Okay, so two aspects of fragments are important. To speed up things after crossing the network link that allows only a smaller size, the IP fragments are not reassembled again at the other side, but travel independently to the final destination. There, they are reunited again in order to form the original IP packet. Each IP fragment contains only a part of the original TCP information. Therefore, only the first fragment contains the TCP part that shows the TCP port number. The other fragments carry the remaining TCP information, but not the TCP port number. What's the poor firewall to do? The arriving IP fragments, except the first one, contain no indication of a TCP port number, so the packet filters can't make a decision based on that, blocking the second and subsequent fragments. This allows all network packets that have passed a network link with a small maximum packet size, reassembling the packet itself and making a decision based on the complete IP packet means that the firewall is accepting all these fragments and storing them until all fragments are arrived and then continue. This opens up a strong possibility that a hacker can make the firewall do a lot of intensive work, especially if the hacker never sends the last packet. The firewall may be so busy with sorting out all these packets that it can't focus on other tasks. This is called a denial of service attack. The attack is like sending Doorman Sam a card that says "see other side" for instructions printed on both sides. He is not going to fall for that. Letting the second and subsequent fragments pass the firewall may be the solution, but this strategy also has a disadvantage. The first fragment can be inspected and is possibly blocked. The final destination computer on the internal network shows that if the first fragment never arrives, it should not reassemble the fragments that did not come through and use the fragment anyway. Some implementations of TCP IP make the mistake of reassembling the fragments, and hackers capitalize on this mistake by sending a complete IP packet that is disguised as a fragment. The firewall allows the packet to pass through, thus relying on the absence of the first fragment. The final destination packet receives this self-advertised fragment and processes it as a complete IP packet. Because the firewall doesn't block the second and subsequent fragments, the hacker is able to send packets to computers on the internal network unchecked. IP spoofing and source routing. Just as you can use a fake return address on an envelope and a fake from address on outgoing email messages. A hacker can use a fake source IP address in the IP packets that he sends to your firewall. This is known as IP spoofing. The firewall should not rely on the source IP address alone to make the decision to allow the packet to pass. By the same token, it's not useful to have the packet filters block packets based on the source IP address. Because the source IP address can't be trusted to be true, the firewall must be able to distinguish on which network interface the IP packets arrive. Packets arriving on the external network interface but claiming to come from an internal IP address should be blocked right away. You may actually get away with this with Doorman Sam. Hi, good morning. Again, my security badge is still inside. I'm merely checking the lights on my car. Why would a hacker do this, and how could he possibly gain advantage by doing this? After all, if he spoofed the sender IP address, he will have a hard time receiving a possible response packet sent in return to the fake address. You'd be surprised. Here are several good reasons from a hacker's standpoint that it's to send a spoofed IP packet. The internal network may already contain a malicious Trojan horse application installed on one of the computers. The hacker may merely want to signal the application to start doing its lowy deed, which is similar to sending a coded message to spy on the inside. The Blue Sparrow will see an early spring tonight. No need to confirm. The hacker may want to stage a denial of service attack against one of the internal computers. The hacker may have temporarily disabled the computer that legitimately uses the spoofed sender IP address and is pretending to answer the now lost return packets at carefully timed intervals. This reassembles those irritating voicemail outgoing messages that some people seem to enjoy, where you think that the person you call actually picked up the phone, but instead the voicemail message contains deliberate pauses and pretends to respond to what you said. The IP packet with the spoofed IP address may actually contain a routing slip that contains IP addresses that the return packet should visit on its way to the source IP address. This is called the source route option. Obviously, the hacker would list an IP address that he is monitoring on the source route list. So I'm going to leave it here this evening for this video. If you like listening, please consider like, sharing and subscribing. Thank you.